So the lithosphere, composition of lithosphere. It's there's a good bit of carbon in the lithosphere. Most of it is biological in origin. However, I mentioned something in the discussion on the atmosphere that was an element that at one point there was a lot more of it that existed in the lithosphere than now, but still most of this element is found in the lithosphere. It is in our atmosphere now. It's the second most common component of our atmosphere, and it's, which is, you guys should all know by now, hopefully, a product of photosynthesis. Oxygen, thank you. So I mentioned when we talked about that, that oxygen is it's not very, but it's a pretty reactive chemical. Not quite chlorine bleach level of reactivity. No thanks. But I would like your attention up here, please. And it's oxygen. And so in the past, before photosynthesis, way in the past, oxygen is reactive with the minerals. Many of the oxygen compounds are solid. Exceptions, of course, being water and oxygen, and carbon dioxide. But otherwise, most of your oxygen compounds are solid mineral materials, and they are combined with silicon and aluminum primarily. So that doesn't mean that the oxygen that's in the crust of the Earth is free oxygen, O2. It is in compounds that are in the Earth. The vast majority of the material of both the crust of the Earth and the mantle, which is the original origin of the crust of the Earth, is silicates, silicon oxide compounds. They will tend to have lots of other stuff mixed in with it, and iron and calcium and all that other kind of stuff. That's what gives us our different rocks and things. But the most part of it is that it is, like I said, it is silicon oxygen compounds or aluminum oxygen compounds, and these compounds all together tend to form quartz. And quartz is your main type of mineral that's found in the crust as well as the mantle of the Earth. If you go to the beach, look at the sand. If you look at it real closely, you've got a lot of different little crystalline colored things in there. But if you were to observe it very closely, you would notice that they, for the most part, all have that hexagonal characteristic crystalline structure that we find with silicon oxide and aluminum oxide compounds, like I said, also known as quartz minerals. So that's most of it, as you can see there, 27%. But then we've got quite a bit of iron, although most of the iron, as we'll see, is in the Earth's core. But quite a bit of iron, calcium, magnesium, potassium, and sodium. What would you say is special about these substances as opposed to the silicon and the aluminum? Any idea why those would be important things in the crust? Do we need those? Do you need iron?
Yes.
Do plants need iron?
No.
Calcium?
Yes.
Magnesium? Okay, so this is your origin of minerals for plants and therefore for the entire food chain. Not the sole one, because we discussed decomposition kind of recycles these minerals, but most of your mineral compounds that make up the bodies of living organisms, starting with plants as producers, putting together, are dissolved bits of these different minerals that are in the soil and that are absorbed by the plants, or dissolved out in the ocean and absorbed by the algae that's in the ocean, the phytoplankton, and then goes up the food chain from there. So that's the key function or the key property of the crust of the Earth that makes it important for life on Earth. And it also highlights the importance of the fact that the crust does, through this active process, does get recycled. So some more basics about the structure. We look at the composition. What's it made out of? How does it react, or what's the kind of the dynamics of this crust? It is active. It's made from about 20 different plates, depending upon some of the plates are kind of like combined into two plates, and so it's generally it's kind of around 20 to 22 tectonic plates. Some of them are oceanic, primarily oceanic plates. These are thinner and denser. So consequently, not only, of course, they're thinner, so they're going to be lower down, but they also sink down a little bit more into the asthenosphere. And so consequently, these are the low-lying areas of the Earth. If we didn't have any water here, these would be the deepest areas. They're in general about 10,000 feet below the sea level, the level of the continents. And of course, since they're low-lying areas, they fill with water, and that makes our oceans. Continental plates just the opposite. Now, You've had many times in the past, theoretically, where the continents have come together and merged and then broken apart. During those times, sometimes ocean crust becomes continental crust, and continental crust becomes oceanic crust, and it gets melted and reformed and all kinds of stuff. So it's not hard definitions, but in general, your oceans, basins at the bottom, they have these oceanic plates, and the continents have a different. The crust itself is actually made of a slightly different material. They are floating on a layer of hot molten magma, which is just lava that's underground, but it is melted rock. It's a melted mantle as well as the components of the crust as it gets recycled and everything through there. That's known as the Lithosphere. And this is the reason for having all the stuff that happens that we have with our geology and everything of the Earth. So there are a few things, about 5 different things really that can happen when these plates interact with each other. Because that's where all this stuff happens. Well, that's where most of this stuff happens, is where they are either bumping into each other or moving apart. And so they will converge. Converge means to come together, right? You guys understand that? Diverge means to split apart. Or they may just kind of slide past each other. Maybe some of them kind of rotate a little bit, so they're sliding past each other. We call that a transform fault or boundary. And when these different things happen, I'm going to show you a table in a minute to break down the different products of the different reactions and where they happen, but you get your various geological formations, volcanoes, deep ocean trenches. So even though you should cross out answers, you were actually correct in this one not being right.
We have no point.
Miss Bozick, so call them the microaggressions though. But also in general, I should put this on here, just mountain formation in general. It doesn't have to be volcanoes. When you have 2 continental plates come together, for example, they push up mountains that don't tend to be volcanic because the crust is very thick there, relatively speaking. And so that's some of the interactions. Like I said, I've got a table for you guys to break those down. Any questions so far about basically the physical nature of the crust of the Earth, both its composition and the way that the fact that it is active and the plates are moving around? They're moving about 5 to 7 centimeters a year, so it's extremely slow. But of course, they are huge and enormous and have a lot of mass behind them. So when they do interact with each other or some other things, there is a tremendous amount of energy that's generated from that happening. Once again, main biological function is the crust of the Earth is to provide soil nutrients, and not just soil nutrients. These soil nutrients are going to wash off into the ocean, and where that happens is where you get the nutrients that the ocean organisms, the ocean food chains need, starting with the phytoplankton. So the other good thing is that because of the fact that they're constantly moving and bumping into each other, we have a rock cycle, which is basically the crust is going to, in a divergent plate, going to come out and make new crust in some areas of the Earth. In other areas of the Earth, it's going to get pushed down, back down into the ascenosphere, where it will melt, and then it can start this whole process again. So there's a couple reasons why this is important. First of all, if you didn't have that happening, these nutrients and everything that were in the rock would get absorbed by the plants relatively quickly. They would move on, either wash out or whatever else, and tend to be displaced, and therefore you wouldn't have that mineral input in the ecosystem anymore. So that would happen fairly rapidly, and therefore productivity in general on land would decrease significantly. Bless you. And eventually would decrease in the ocean as well, because that's where the ocean is getting its nutrients, is from the land. The second thing that would happen is that without new mountain and landform formation, the processes of erosion would wear down all the landforms and everything and erode them, and they would all have been eroded into the oceans by now, and the Earth would be one big ocean. And so that, of course, would reduce our biodiversity and all kind of things, and all the kind of things that happen from there. So these are ways, like I said, these are ways that reason why all this geology stuff is important for life on Earth. The way that all that happens is as a summary of it. I've got a diagram, but your weathering is where The mountains and other landforms that have been pushed up are broken apart by wind and rain and ice, and then the erosion is actually where they get washed out. And this is an important part of the process. This is how, like I said, remember I said we were going to look at how the hydrosphere and the atmosphere also interact with the lithosphere. This is where it happens in this part of the rock cycle, because the wind and water, that's of course with the hydrosphere and the atmosphere, they break apart and then disperse and wash out or blow. I said like the wind, the atmosphere, the dust storms and stuff serves to distribute nutrients. But then of course the rains, as they wash down the mountains and things like that, and settle in and spread out, they distribute nutrients in that way. And so that's, like I said, that's an interaction of the hydrosphere and the atmosphere with the lithosphere, with the end product being a distribution of nutrients and therefore helping living organisms. So you get that erosion, it gets washed out, it flows down through the rivers, it gets blown by dust storms, whatever, it will tend to settle in or deposit in your low-lying areas. A lot of times these areas are wetlands, and that's why wetlands are particularly fertile. And of course we tend to interrupt these processes when we divert water and things like that, but that's a subject for another day. But that's a very important part of the whole distribution of nutrients and everything throughout ecosystems, throughout the earth, throughout the biosphere. And then eventually they will wash down into the ocean. Everything ends up going out into the ocean eventually, and down on the seafloor where they can go through what's called subduction. And we'll look at that more in detail when we look at the table, but that's just the process where one plate is pushed underneath another plate, and when it happens and it carries that crust along with it and all the sediments and everything that have deposited upon it, it gets pushed down into the asthenosphere, into the magma, and gets melted, and then it can start the whole process all over again. So that's the cycle part of the rock cycle. Very long cycle, but a cycle nonetheless. And it goes through the different igneous, metamorphic, and sedimentary rock phases. I'm not going to go into that now. That's why I give it to you the vocab word. You should know those, but we don't need to have those details memorized right now. So any questions? Any questions about the rock cycle and how that functions to distribute nutrients around the world? No? All right, good. This next part here is not actually about the lithosphere, but it is part of the rest of the solid part of the earth, and it's important for the earth in general. So I decided I would go ahead and give that to you now. It is most of the structure of the earth is called the mantle. It's a very thick layer of actually semi-solid rock. They have determined that the mantle, even though if you looked at it and everything, it would be just like rock, it is actually moving very, very slowly, centimeters a year, just like the tectonic plates. It's convection. It's the parts of it are rising and pushing it forward. Now, at the top of the mantle, the mantle is hot. Okay, let me say that first of all. And this is another one of those things that is a unique property of Earth. Hopefully you're seeing a trend here in that there are a lot of unique things about the Earth that make it very livable, but we actually have an abundance of radioactive elements, particularly uranium. And that would seem bad, and some say that may have an influence on mutation rates and cancer and stuff like that. But what it does, of course, is radioactive elements give off heat. And so the mantle is very hot. It's going to be hot because of pressure anyway, but it generates even more heat than, say, another planet of our size would if it didn't have radioactive elements in it. So the mantle is very hot, but it is made out of materials. If hopefully you remember, I talked about the fact that water is very unique in the fact that compression actually hinders it from freezing, or keeps it in general from freezing, whereas most substances, pressure makes it freeze. So in other words, keeps it a solid. So the mantle it's a very thick, almost liquid, but the pressure of the earth upon it keeps it in that almost crystalline state. But once it gets up near the top, then the pressure is low enough that it can actually melt. That's where our asthenosphere comes from. But then you think, well, why isn't it molten all the way to the top then? That would make sense, right? It's the lowest pressure up here. Well, that's where our water kicks in. And the fact that we've got an abundance of water, of course being a big heat displacer, and the theory is that when we first got our water, perhaps from comet impact or something like that, that you did have a molten surface, but then the water being on that surface would evaporate and condense and go back and go through, do its water cycle thing, and dissipate all that heat energy. So consequently, that ended up cooling the outer layer, so it solidified into the rock that we now have as our crust, but we still had enough heat generated underneath to have a molten layer underneath. Very similar to fried ice cream, which is awesome stuff if you've never had it, but it's kind of got a crispy cone on the outside, and then the ice cream underneath is slightly melted, and it is amazing. So maybe one day aliens will eat us thinking we're fried ice cream. So anyway, under the mantle, you get to another, here we go again, unique property of the Earth, and the fact that we have a liquid layer, and this is also a product of liquid layer of iron and nickel. This is also a product of the fact that it is hot down there, and basically this is concentrated down there because they're fairly dense elements, and so and there's a lot of it in the Earth, and so they sank to the core of the Earth. But we have a solid and liquid, and the reason why we have a solid and liquid is that the temperature is high enough for the outer core to be melted, and the pressure is also low enough, even though the pressure at that level is crazy intense, extremely, gigatons per square inch. I'm probably exaggerating, but it's extremely heavy, of course. But it's light enough that they do have a melted layer, but then once you get to the core of the Earth, those pressures are so high that it's too much pressure to freeze, or not to freeze, too much pressure to be liquid. So anyway, why is that important? Is the fact that with that inner core being solid, it rotates inside the liquid core, and same basic composition, mostly iron, by the way. There's not that much nickel in there, but enough to be of a significance. And so that inner core rotating inside the liquid core, being both metals, sets up a kind of like a dynamo generator kind of thing, which basically creates a magnetic field. So it makes the whole Earth like a big magnet. And that's good for us because we wouldn't have compasses without it, but it's also good because it shields us from high energy radiation from the sun. In particular, the charged particles of the solar wind that is constantly flowing out from the sun. Theoretically, once again, just like we didn't have an ozone layer, life would not be able to exist on the surface of the planet. Same thing without our core, without our magnetic field to shield us as well there. So there we go again with another great thing about planet Earth that allows us to live the way we do. Did I spell that wrong? Radiation. No, that's weird. And then finally, it's kind of like a end node post-on thing, but keep in mind that a lot of the bedrock, a lot of the crust material is not just geological in origin, as we know, particularly here in Florida. I will take fossil, it is that, but more specifically, marine organisms. So coral and clams and other shell-bearing organisms that have built up when you have areas that were underwater but somewhat shallow enough for these particular creatures and stuff to collect in those areas, they build up. Calcium carbonate builds up. That's the main element, is calcium in there. And you have what's known as limestone. And it could be that they get raised up, so you may have limestone way up in the mountains like you do in the Alps in France. Also parts of the Rocky Mountains have got limestone because at one point they were underwater. So it can make a pretty significant part of the bedrock in different areas. Any questions? No? Okay.